Welcome, I'm Carl Tate. Benioff zones are earthquakes within subducting plates. This is our map showing all earthquakes in the GCMT catalog here since 1976, magnitude 5.5 or greater, about 19,200 earthquakes. And we see how the earthquakes show us the plate boundaries, but we can now look at some subsets of these. So this is showing all depths. And now we can look at, most of them occur shallow in the crust. In this case, it's at 100 kilometers, anything shallower than 100 kilometers. Next, we'll look at the deep ones. And there things get pretty simple. So this is the entire planet of earthquakes deeper than 100 kilometers. And seismologists have known about and recognized these deep earthquakes for a long time, and long before plate tectonics was figured out. So these zones of deep earthquakes are known as Benioff zones. You can check out the end for some history on their discovery. So let's put the continents back on to see what we're looking at. And the plate boundaries. So Benioff zones help define subduction zones where the one plate subducts beneath another. So all of these dots are subduction zones. We're actually looking at activity within the plate that's being subducted. So notice how in this map view, the dots are shifted away slightly from the plate boundary. Well, that's because this is the Pacific plate. This big old Pacific plate is subducting under Aleutians, Alaska, Kamchatka, Japan, Marianas, Tonga, Kermadec. It's subducting to the northwest, to the west here. And what we're looking at is the activity and deformation inside the plate as it goes downward. So that's why the dots aren't exactly on the plate boundary in the case of subduction. Same in South America. All the dots here represent subduction, or in this case, deep collision between two continents. So let's check out Alaska here. We can already see some of the dots representing these significant earthquakes that are deep. And here's a map of the earthquakes in Alaska provided by the Alaska Earthquake Center. There's some inset maps that we'll look at here and focus on. So we look in here on the legend. First, we notice that they're colored by depth. So the darker maroon are below 100 kilometers. So that's the category I was just showing you. And we can see them here along this entire arc here. The red ones are in the crust, and these yellow ones are intermediate depths. So this helps illuminate the kind of a picture of one plate underneath the other. So what we're just looking at, earthquakes as a function of depth, but we really want to be looking at this and saying, aha, that's the Pacific plate underneath as it goes down. And it's much easier to see if we look at the two cross sections featured here, A and B. This is shown on this part of the map to try to explain, the occurrence of so many earthquakes in Alaska. It's really, many of them are actually under Alaska, beneath it in this Pacific plate. So here's cross section B out in near Adak, and it's showing, again, the dark are the deeper earthquakes and the red ones are the shallower ones. So we kind of generally see this red to yellow to maroon pattern. And if we look at the cross section from this part right here, is that the trench? So it'd be from the south to the north on the left side. We can see the depth. This is 50 kilometers. And this is showing you an actual profile of the Pacific plate, and it comes in and dives down under Alaska. This figure is also showing where the volcanoes occur relative to the subduction zone. But here you can see the coloring here more clearly, that they're colored at 100 kilometers is one color break, and the other one was, let's just check, was at 35 kilometers. So that's where the color changes. But you can see that this picture is much easier to understand when we look in the cross-sectional view. And that's why this topic follows sort of our summary of evidence from the surface of plate tectonics, because this we really need to start thinking about a three-dimensional explanation, and for why these Benioff zones exist, well, we now know they are defining the downgoing plate. Here's another cross section. This is pretty much through Anchorage in a very different area. You get some sense of how varied subduction zones can be. So in this area you have what's called a flat slab. It's just kind of peeled underneath the North America plate. The Pacific plate comes in and it says wide locked zone. There's Anchorage, and then here it comes away, and this would be the Benioff zone. So the Benioff zone, it really characterized the deeper earthquakes, but you can think of it as all of the earthquakes within the subducting plate. All of this could be considered Benioff zone, but it's certainly that anything below 100 kilometers on this planet is within a subducting plate. So you can look all over the world. This is a representation of this is the westernmost solutions here. This is Kamchatka going down into Japan, and this is showing some cross sections here of a subduction zone, and really just looking at the seismicity to help define the geometry of this downgoing plate. And so part of this second part is looking at other Benioff zones, but also how they can be used to get a complete picture of the geometry of one plate going beneath the other. So this is from in this direction, and now here we're going down to 700 kilometers. So this depth to slab and color is giving you a picture of how deep the earthquakes are. In Alaska, it's more like 200 to 300 kilometers, but in other parts of the world, they can be as deep as 700 kilometers. Here's a cross section under northern Japan. It's not as steep as you can see here. Shows the dots, and then also the dashed line is the surface that's used in this cross section to get a picture of the 3D geometry. And then this would be the third one shown here. Again, you have this line of earthquakes that are occurring within this plate as it dives back into the Earth's mantle. So these Benioff zones can be used to determine the subduction interface, which is the interface between the downgoing plate and the overlying crust and mantle. So this colored region represents a surface that it's entirely below the Earth's surface. So when we look at these, we have to be thinking this is something underneath that's cutting through the Earth, but it is, essentially it's the top of the Pacific plate after it goes through or under the trench, as shown right here. And taken together, this shows the location and geometry of the world's subduction zones, principally defined from these Benioff zones. So this is the Aleutian, Alaska subduction zone. This is the Cascadia, where Juan de Fuca subducts beneath North America. This is Cocos Plate, South America, Tonga Kermadec, and so on. So this is a really terrific picture of not only where the subduction zone and convergent boundaries are, but after these plates meet, what is the shape of them as they go down into the Earth's mantle. And here's an aside. You can skip this if time is short, but it's kind of interesting to see how these ideas arise. And here you'll also see this Wadati-Benioff zone, and we'll see why Wadati is a major player. Wadati's first paper in English was in 1928, describing these deep earthquakes in Japan. And there's this really a remarkable picture of contours from 1935. This is Japan. And these are contours of depths of where he determines these earthquakes to come from. He sees this systematic pattern that they're as you go farther away, they tend to be deeper. And if you superimpose this on the modern view, and I'll just show here, go back and forth. I mean, they're not exactly right, but it is incredible to me that in 1935, with the kind of data and understanding and not even knowing anything about plate tectonics really, that they were getting information that turns out to be really an essential part of understanding plate tectonics. With everything about how plates move understanding these deep seismicity zones was a critical piece. In 1949 was the paper for which the term Benioff zones comes from. This shows a map view of Tonga Kermadec, if you see the longitude and latitude. So here's 5 degrees, so that'd be 500 kilometers. And this is showing in map view the dots. Again, the dots are west of the trench. We now know, that the Pacific plate here is subducting at this Tonga Kermadec trench, and these were called ocean deep. Ocean deeps is what we would refer to as trenches now. And Benioff has the critical connection between the ocean deep, which is the trench, and the seismicity. So this, it's scattered. This is 1949, but he's saying there's earthquakes down to 700 kilometers, this Benioff zone, and there must be some link with the ocean deep at the surface. And so Benioff tried to understand that and had this picture sketch illustrating the proposed origin. And he thinks of 2 materials that are coming up against each other, that ram up against each other, but push in a way that creates this major fault while also forming the trench at the surface. You have the meeting of 2 materials, head-on collision here, that forms possibly this massive fault. Well, that's turned out to be wrong, but it's still interesting to explore the ideas that people had and realize that what we actually have as plate tectonics is an incredible and even beyond the imagination of some of the greatest scientists who are looking at these problems. So 18 years later, a paper kind of culminating all these seismic observations, seismology and the new global tectonics, we have this picture of, one plate lithosphere going down under the other and exploring and pointing out where this S, being the S standing for seismicity, mostly within the crust as it subducts beneath the plate, but trying to understand it's not that all the earthquakes that Benioff was looking at was on some master fault. It's actually in this plate bending and deforming as it goes down. So this is a pretty good picture of what we understand today of a subduction system and also the creation of the volcanoes as well. In that same paper, figure 1, showing a pretty famous picture of the configurations and roles of the lithosphere. That's the rigid, the plate, the asthenosphere, the weak layer that the plates ride on, and the mesosphere, basically the mantle, in which the lithosphere, a layer of strength, plays a key role. And we will look at these structure properties very shortly in the next talks. But the point here is that by 1967, through seismic observations, subduction and the understanding of the Benioff zone was coming into picture. So here's spot the 3 types of plate boundaries. There's the spreading occurring here where the arrows are pulling apart. These would be the transform strike slip segments where the ridge segments are offset. The active strike slip boundaries are shown here in between. And then, of course, the main one here is the convergent settings where one plate is going down. And this would be the deformation in these downgoing plates shown here would be forming the Benioff zone. So the takeaway topics: Benioff zones are locations on Earth where the deepest earthquakes occur. The deepest earthquakes occur at about 700 kilometers below the Earth's surface. Earthquakes in Benioff zones occur within the downgoing, subducting oceanic plate. And Benioff zones occur in subduction zones.